Hello students, welcome back to this lecture series on VLSI design KEC 072. This is lecture number 15. I am Dr. Raman Kapoor, Associate Professor at Department of ECE AVS Engineering College. This lecture I want to continue with my topic on sequential CMOS logic circuits. Consider this as part 2 of this topic. In the previous lecture, I have explained or introduced you to what are sequential logic circuits, how sequential circuits differentiate from combinational circuits, that memory or storage element is the major difference or the major distinction between a combinational and a sequential circuit. Okay. So, if you remove the memory, if you remove the storage part from a sequential circuit, you are left only with a standard combinational block. Okay. So, if you store the data, by data I mean the current state of the output is being preserved or latched onto a certain circuit, so that it can be used at a later stage, okay, for processing, for obtaining the next state of the system, that is the storage element of any sequential circuit, which is the heart of a sequential circuit. So, that is why most of the analysis, most of the discussion of a sequential circuit is generally related to how data is being latched onto. Okay. So, when we differentiate between different sequential circuits, then also we are actually differentiating between different types of memory circuits. Okay. So, we have done one distinction between static and dynamic memories. Static memory or a static sequential circuit, a circuit which has static type of memory, is the one which uses simple positive regeneration from the output to the input. So, whatever is available at the output is fed back as it is to the input, okay, and it is generally always available as long as the circuit is switched on. Okay. So, consider this circuit here, where you have an inverter which has an input, say call it Vi1, it inverts its input, produces an output VO1, that output is serially fed to another inverter, okay, and it produces another output. Okay. So, Vi1, VO1 are inputs and outputs of the first inverter, Vi2, V02 are the inputs and outputs of the second inverter, and the connection is such that V01 is equal to Vi2. Now, if this second output is fed back again to the input of the first inverter, so that basically means that when V02 changes, it automatically changes the overall input of the entire circuit. Okay. This type of a circuit is very famously known as a bistable latch, okay, or a bistable circuit which performs the latching operation. Why is it called bistable? That will be clear in a short while. We know what is a bistable circuit, which is stable at two different values of outputs. Okay. And since we are talking about digital design, the two options are only 0 and 1. So, a system which is stable at 0 output and is stable at 1 output is a bistable circuit. Okay. So, let us compare the VTC or voltage transfer characteristic. It is nothing but a graph between the output voltage on the y axis and input voltage on the x axis. That V out versus V in graph for a digital circuit is also referred to as a voltage transfer characteristic. Okay. So, consider the voltage transfer characteristic of each inverter. This is inverter 1. So, this is your output V01, this is the input Vi1. Okay. Now, because you are applying the output of first as an input to the second, you can put the V out 1 here and Vi2 here on the x axis. So, this is basically an inverted or a rotated graph, rotated VTC for the second inverter. Okay. If you draw in a common way or the most generalized way, you will see a similar graph between V02 and Vi2. Okay. So, here you have a rotated graph between Vi2 and V02, okay, and Vi2 is equal to V01. So, output of first stage is equal to input of second stage. This is just a rotated graph. And another benefit of rotation is that when you combine these two graphs, the resultant graph is very easy to understand. Okay. So, this plus this is equal to this. Okay. So, you have added these two graphs, plot them on a same graph, same single graph, 2 dimension. Okay. And then you see that the graph looks something like this. So, this is the voltage transfer characteristic of your bistable latch circuit. Okay. Now, see, I have defined 3 different regions of operation. This is known as point A, this is known as point B, and this is known as point C. At point A and point B, these are your so called bistable states. At this point, either at point A or point B, either your Vi2 is 1, here V02 is 0. Okay. So, here this is a stable 1, A represents stable 1 and B represents stable 0. Okay. At point C, this is the point of instability, also known as a metastable state. If you tend to bias your bistable circuit at point C such that you have given input bias, so that the circuit becomes triggered at this point, the energy at this point is so high, the gain of the inverter circuit is so high that the output either switches back to A or back to B, okay, which basically means that at any point of time you are going to see at least one stable state, either stable A or stable B. Okay. At point C, it is a metastable point, it is the point of instability, and your circuit more often than not immediately shifts back to one of the stable states. Okay. This bistable behavior of your coupled inverter circuit can also be studied if you see the energy distribution. Okay. So, you have this inverter 1 Vi1 giving V01 passed on to second inverter, so that its output is fed back. Okay. This is how the voltage transfer curve looks like. This is your unstable point, these are your stable states. If you see the potential energy graph, the energy at point C is quite high. Circuits tend to reside or stay at low energy state, that is the preference. Okay. Lower energy states are usually occupied earlier, okay. And even if a circuit is at a high energy state, it tends to shift back to lower energy state. So, a circuit biased at point C will either shift to point A or point B, resulting in a stable operation. Most of the sequential circuits and many of the examples which we are going to see throughout these lecture series are actually bistable synchronized sequential circuits. Bistable means they give a stable 0 or a stable 1 at the output. Synchronized means that they follow some kind of a clock, and the trigger or the level of the clock decides when output is going to change. And sequential circuits, we know something which stores the data, stores the current state, so that next state can be decided. So, this circuit, this bistable latch is what is our building block, our starting point for studying sequential circuits. Okay. And let us see how CMOS implementation is done. So, you can have an inverter here. So, P type pull up network, your N type pull down network. Okay. So, when this input becomes high, it gets pulled down, when it becomes low, it gets pulled up, that output gets transmitted to another one, and the output of that circuit goes to the input of first circuit. Okay. And if you see the output, okay, output high, output low, right, the output 1 or output 2, output of the first inverter, output of the second inverter, they converge or they diverge to the stable states, okay, either a stable 1 or a stable 0. Okay. VOH is output high level, VOL is output low level. Right. Now, using that bistable element, that basic connection of two inverters connected in cascade and coupled together, okay, use that as a basic starting point, and instead of inverter tried different logic circuits. One such mechanism, and why we are basically doing it, if Vi1 was 1, if you look at the bistable circuit again, if you had a 1 here, you would obtain a 0 here and you will again get a 1 back. So, logic 1 is being stored or latched onto. If you had a 0 to start with, you will get a 1 here and then you will again get a 0 here. So, 0 is being latched onto. So, this cross coupling connection is actually doing nothing but a latching operation, it is storing the data for you. And why do you need this storage? Is for that memory element of the sequential circuit. Okay. This is one of the most basic mechanism of how you latch onto the current state of the system, preserve it so that next state can be decided. Okay. And use this mechanism. So, instead of inverter, say use NOR gates, and the resulting structure is what is known as the most common SR latch or set reset latch. SR in SR flip flop or SR latch stands for set reset. Okay. Instead of inverter, we use a cross coupled bistable NOR gate circuit. Okay. So, you have one NOR gate here, this is your schematic, and another NOR gate here. One of the input is your S input, another input is R input to the next NOR gate. Second input of this NOR gate is coming from the output of this NOR gate, cross coupling, and the another input of this NOR gate is coming from the output of the previous NOR gate. Okay. So, Q is basically Q output is basically an NOR operation between R and Q bar, which is complement of Q, and Q bar is a NOR operation of S input and Q output. Okay. Every flip flop and latch circuit generally gives you both output and its complemented form also. Okay. This is the symbol, you have two inputs S and R, you have two outputs Q and Q bar. Just note here that I have not added any clock or enable symbol as yet. Okay. There is no pin showing you clock or enabling point as yet. Okay. I am just showing you the latching operation right now. So, whatever you have input, how it is being changed or how it is being altered at the output. Okay. This is the characteristic or truth table. When both S and R are 0, they just preserve their previous value, latching operation. So, this is known as latching or storage operation. When S is 1, R is 0, output Q goes 1. So, this is set operation. For 0 1, this means reset operation. The only issue is that if you put both the inputs as 1, if S and R both go to 1, then if you see the output of a NOR gate, both the outputs will try to become 0. Okay. So, there is a race between both to become 0. So, the way you have connected the wiring, the respective propagation delays, one might overrun the other. Okay. So, there is a constant oscillation, constant race going on between two outputs to obtain same logic level when they should be complementary. So, this is a forbidden state. Okay. This is how it is done in a CMOS implementation. So, you have a NOR version. So, you can see a series combination of PMOS, parallel combination of NMOS, series in PMOS and parallel in NMOS, the simple NOR gate circuit. The only difference is that the output of this goes as input here, the output of this goes as input here, cross coupling. Okay. And if you see the operation in terms of transistors, when S and R are at output high, output low respectively, M1 and M2 is on, M3 and M4 are off. Okay. This is M1, this is M2, this is M3, this is M4. Vice versa, when S is at output low, when R is biased at output high, okay, M1 and M2 become off, right, and M3 and M4 become on. Okay. if both are biased at output low, we are not considering output high because that is for both, because that is forbidden. When both are at output low, there are two cases depending upon what was the previous output. Okay. So, in some cases either M2 will be on or M3 will be on. So, if you had a 1 here initially, M2 will be on. If you have a 1 here initially, then M3 will be on. Okay. But M1 and M4 will always remain off. Okay. So, depending upon the previous state, one of the transistor either M2 or M3 is going to be turned on. This is how latching operation is done. Till now, this is just a simple latch. It has not taken, and this is how you can do the same thing. You can do the same implementation of SR latch using NAND gates. So, instead of cross coupling NOR gates, you can use NAND gate also. The circuit remains same, working remains same. The only difference is that a NAND gate SR latch responds to active low inputs and a NOR gate SR latch responds to active high inputs. So, when SR are high, okay, then your NOR as active high basically means that they will be true when the signal supplying them or the wire supplying them is at high voltage. Okay. So, NOR gate SR latch is an active high component, a NAND gate SR latch is an active low component. Okay. Now, till now we have seen how that bistable circuit or SR latching is happening, but still we have not included the clock or some kind of a leveling, some kind of a trigger. For synchronous operation, you need clock or you need at least an enable switch, a switch which turns on and off. When it is on, data gets latched or written, and when it is off, the enable is off, the data remains latched. Okay. So, for that you add extra pin. Here I have shown a clock signal here. Okay. So, this is your same NOR based level sensitive SR latch. Okay. Here you have added another transistor here which is connected to clock. Okay. The output here Q is going as input here, the output Q bar here is going as input here. Okay. So, here you see when clock goes high, when clock is 1 here, suppose S is 1 and R is 0. Okay. So, in that case there is a path for your Q to charge here. This R equal to 0 provides a path for it to charge. Okay. So, if Q has to go, and if say initially Q was 0 or Q bar was 1, they are complementary, this Q bar will turn this transistor on, this R equal to 0 will turn this transistor on. Okay. So, for Q point there is a path to charge and this turns to 1. Okay. And this is only happening when clock is 1. When clock goes to 0, if clock goes to 0 here, if clock is 0, so this transistor is off, this is off. Okay. So, basically you will not find a path from this end, you will not find a path from this end. Whatever is the logic level present at S or R, that remains the same. There is no path. Suppose Q was 1 and Q bar was 0. Okay. If Q was 1 here and Q bar was 0, okay, and when clock is off, you put S equal to 0 and R equal to 1. Now, there is no other path left, there is no path left for Q to discharge here. Okay. And if Q is 1, there is no path here also, this PMOS is also off. So, there is no path left for Q bar to actually charge to VDD. Okay. So, when clock is 0, if clock is at logic 0, this NMOS is off, this NMOS is off. Suppose before this clock going 0, Q was 1 and Q bar was 0. Now, Q will not find a path to discharge. Okay. Q bar will not find a path to charge. So, even if your S is 0, R is 1, as per truth table your Q should go 0 and Q bar should go 1, but because you are giving a level triggering via the clock, okay, and that clock is off. So, this is positive level triggering. Okay. So, in this case the clock actually avoids the data to be updated. Until the clock triggers, data will not be, output will not be updated. So, this is how level sensitive latching operation is taking place. Okay. So, any kind of a latching operation requires some kind of a trigger, which is generally the level at enable or clock, okay, and that basically decides whether data will be updated, output will be updated, or output will be latched only, okay, or the previously latched data will remain. This is how level sensitive latching works. A major drawback of the SR flip flop was when both are 1, the outputs tend to be at same logic level 0, which is not allowed. Solution to that is the so called JK flip flop or Jack Kilby latch. Okay. I am using both the words flip flop and latch. The difference I have already explained in the previous lecture. Latch is level sensitive, flip flop is edge triggered, okay, but they are both doing more or less the same thing. They are doing storage aspect only of a sequential circuit. Okay. So, for the SR circuit, if you use NAND gates at the input in such a way that the inputs to this NAND gate is your J input, Q bar and clock. Okay. So, if I call it N 1 and if I call this as N 2, then N 1 is basically equal to J dot Q bar dot clock NAND operation, okay, and N 2 is your K input, Q output and clock NAND operation. Okay. So, when both J and K tend to be 1, the output keeps on toggling. Okay. That toggling oscillation exercise keeps on going. In SR latch it was more of a race, here it is more of a toggling operation. Okay. How it is implemented? So, this is the circuit which is using the CMOS approach towards implementing a JK latch. Okay. So, you have J input here, you have K input, clock and clock here. Okay. The clock is also connected here. This point is giving you Q output and this point is giving you Q bar output. Q is applied as an input to this circuit, Q bar is applied as an input to this circuit here. Okay. So, see the circuit density has slightly increased, the number of transistor has increased, but then you also solve that problem of when both the inputs are 1, what happens. Okay. So, in this case suppose clock is triggered, okay. If clock is 1, okay. So, this NMOS is on, this NMOS is on, okay. Both are on here. Suppose J is also equal to 1 and K is also equal to 1. So, this NMOS is on, this NMOS is on. Suppose Q was initially 1 and Q bar was 0, they are complementary to each other. So, Q was initially 1 and Q bar was initially 0. In this case, Q has a path to discharge here. Okay. This being 1, this PMOS is off, this being 1, this PMOS is off. Okay. This Q now has a path to discharge. So, Q instead of 1 goes to 0. When this goes to 0, this point here, the input applied here goes to 0 and then there is a path for Q bar here to charge. Okay. So, when both J and K are equal to 1 and clock is triggered, if suppose Q was equal to 1 initially and Q bar was equal to 0 initially. Okay. So, in this case Q and Q bar can toggle, the output which was high gets a path to discharge, the output which was low gets a path to charge and this oscillation keeps on going. It is not that this toggling happens only once. If the clock period is high enough which covers many propagation delays of the circuit, this toggling will keep on happening. If the time period of the clock, if the positive half cycle of the clock is very large and the propagation delay of logic gates is less, that would basically mean that once Q and Q bar have toggled, they can retoggle again. So, this oscillation between 1 and 0, 1 and 0 will keep on happening provided J and K are equal to 1. Okay. This solves the problem which you had in the SR latch, where when both S and R were equal to 1, both the outputs raised towards having the same logic level. At least here they are both complementary to each other. Okay. This is how a JK latch is implemented in a CMOS circuit. Finally, we have another type of latch which is known as D type of latch. Okay. So, if you in your course on digital electronics, you would have read about different flip flops and latches. So, you have SR, you have JK, you have D type and T type. The most commonly used storage element is actually the D flip flop. Okay. D or D latch. D in this latch stands for delay, meaning that the same whatever signal is present at the input is latched onto the output when the latch is enabled. The only thing is that when the latch becomes enabled, the amount of time which has passed, the delay which has passed, only for that time it stores the previous value. That is why the word delay or D latch. Okay. How it is implemented? It is a very simple approach. You use what is known as a transmission gate. Okay. Transmission gate is nothing but a way of a multiplexing operation. You have a PMOS and you have a NMOS. Okay. Now, they both are complementary to each other. One triggers on high voltages, another triggers on low voltages. Suppose clock is 1, so clock bar becomes 0. Whatever is present here will either go here or it will go here. Okay. These circuits, either one of them pass a strong 0, another one passes a strong 1. Okay. So, whether D is 0 or 1, it will be passed through with equal intensity. Whatever is present at D will be transmitted at the input. It gets inverted here, this is D bar, it gets again inverted and it is equal to D. So, this is how the same input gets latched onto the output. When the clock is opposite, suppose when the clock is 0, then clock bar becomes 1. So, this becomes off, this transmission gate becomes off. Okay. In this case, this PMOS is off, this NMOS is off, D can never enter this circuit. This is like a switching mechanism, but Q enters this transmission gate and it is passed on to here. So, Q enters, so you get Q bar here and it again gets inverted and you get Q. So, what is basically happening? The passed output is getting latched and it is getting held, right. When the clock is high, when the clock is enabled, this switch allows D to enter, but this switch disallows Q to enter. So, whatever is entering here gets inverted here, gets inverted again. So, if D enters, it first gets inverted here and then it again gets inverted, so that the same input gets written to the output. For the opposite clock cycle, this switch is open, this switch is closed. So, Q is fed back, again the bistable element with positive feedback, whatever is at the output gets fed back to the input, right. That signal goes to the input and is again available at the output, the so called storage mechanism. Okay. So, with this I come to the end of this lecture. I have given you an implementation overview, how latching works, what is a bistable element, how data is latched onto, how memory can be implemented in a sequential circuit. We have done it from the point of view of a latch. Now, we need to move further in our following lectures and see how actually a flip flop works. Okay. So, with this I end today's lecture. Thank you.